we're going to see an example of this integral test. All right, so to do the integral test, there are 3 requirements. First, we need to see if this is positive. Is it positive? Well, let's see here. In this example, f of x is going to be x over x squared plus 1. So and these are the requirements for f of x. Is f of x going to be positive? Well, the thing we got to keep in mind here is we're only considering, if you will, when x is greater than or equal to 1. So if I'm plugging in anything greater than or equal to 1, well, that'd be like the first one would be 1 over 1 squared plus, that's positive. I mean, it's going to be positive, right? I'm plugging in positives. Everything is positive. So that looks good. Check. The next thing that I need to check here, so that would be, let's say, number 1. Oh, we need to check to make sure it's continuous. Is this function continuous, again, when x is greater than or equal to 1? Well, again, if everything I plug in there is positive, there's never going to be a 0. In fact, it could be 0. There's never going to be a D and E, is I guess what I'm trying to say. Nowhere is this thing going to be discontinuous. In fact, this particular function is continuous for all real numbers, and in particular, it is continuous when x is greater than or equal to 1. The third requirement is the hardest one to kind of deal with, and the third requirement here is we need to make sure that it is decreasing. So this is kind of the tougher one, and so I'm going to cheat here just a little bit. How do we tell if a function is decreasing? Well, we look at its first derivative. And I'm going to cheat here. I'm actually not going to use the quotient rule. I've already done the derivative just to speed this process up. You'll get 1 minus x squared over x squared plus 1 squared. Well, I claim, now remember, we're talking about when x is greater than or equal to 1. Now, when it's exactly 1, this turns out to be 0. So that's not great. However, once I get past this, this is going to be less than 0 once we get past 1. So once x is equal to 2, this thing just keeps going down. In fact, it's going to go down negative. It's all the answers are going to be negative once you get past 1. So it's starting at 0 and it's essentially going down. So it's decrease. And we're talking about the first derivative. I'm not talking about the value of the function. So that means that this is also a yes. Oops, I guess I should do right there. Now, guys, there's other ways for you to check that. Like you could have just graphed this function and looked at its graph from 1 forward, and you would see that it's decreasing. This is kind of the formal way, though, if you needed to check to make sure it's decreasing. So all of these requirements are a check. Therefore, we can try to use the integral test. Now, here's the bad news about the integral test. In order to do the integral test, guess what you have to be able to do? Integrate. So the question is, can I integrate this thing? So can I do the integral from 1 to infinity of x over x squared plus 1 dx? Well, first of all, hopefully you remember we did a section in chapter 7 on improper integration, or improper integrals, because that's what this is. So the first thing we're going to have to do is we're going to have to do the limit as b goes to infinity, the integral from 1 to b of x over x squared plus 1 dx. Now, does anyone happen to know how we will be able to integrate this guy? And please unmute yourself when you say how.
Use substitution.
Oh my gosh, James, you had this moment. It was right there.
Use sub.
There it is. That's what I'm talking about, James. First of all, James, good job. Gold brick, buddy. You got the right answer. But whenever I want you sub, I want to hear some enthusiasm, James. You sub. So we're going to do some U sub here. And if you guys don't mind, I'm just going to write what U is. U would be x squared plus 1. Du would be 2x dx. But guess what we're going to do with the 2? We're going to divide that over to the other side, okay? And I'm kind of skipping over the integration part here because I want to get really into the meat of this. I don't want to spend a lot of time reviewing integration, is I guess what I'm trying to say. So this integral is going to basically be 1/2 the limit as b goes to infinity of the integral from, oh, I guess I need to be careful here. What does 1 change to?
2.
It's going to change to 2 because you're going to plug this 1 into here. So that's going to make that 2. Infinity is still going to be infinity, so that's okay. But now we're just basically going to have du over u. And of course, that's going to give us the natural logarithm. And I'll leave the limit thing in here. B goes to infinity. We've now got the natural logarithm of u, and we need to evaluate that from 2 to b. Notice I didn't put absolute value here because b is, or 2 is positive clearly, and infinity is positive, so I don't really need the absolute value here. Now, guys, you realize I can stop now, right? What's going to be the value of the natural log when I plug in infinity? It's infinity. Half of infinity is still infinity because any number times infinity except for 0, we don't talk about that, is infinity. So at this point here, we can just, I'm going to do it in red. I'm going to put that this goes to infinity. And so I'm going to say, therefore, I'm going to abbreviate this series diverges by the integral test. A hand went James.
I think I forgot why we changed the bottom one to 2. Why do we do that again?
Yeah, the good question. And guys, if I skip over something and James is like, okay, and I appreciate you paying attention, James. Please just raise your hand or unmute yourself. So remember, we're converting this improper integral via u sub, right? So we're literally changing the variables for the integral. Up here, this is essentially saying that x is equal to 1. But now we're no longer talking about x. Now we're talking about an integral in terms of u. So when you plug x equals 1 into this piece right here, well, 1 squared is 1. 1 plus 1 is 2. So when x is 1, u is 2. U2. Joshua Tree. Shoot, nobody got it. All right, moving on.
I got it, Mr. Allen.
Thank you, Ridge. I was getting very sad there. I was realizing how old I am. You guys realize I'm going to be 50 this year, right? So Mr. Allen's like getting super old here. So when I say stuff from my 80s and 70s, background, I'm sorry. I should not expect you to know that, but Ridge, you've just earned a mental gold brick in my head because you knew what I was talking about. Okay, moving on. All right, so let's look at example 2. I'm going to maybe move a little bit more quickly through this one. And the reason I'm going to move more quickly through this one is when I say that, I'm going to kind of skip over the conditions, if you guys don't mind, okay? The conditions are all met here. I hope you guys can see this is very similar to the last one. So I'm going to just write, conditions, check. Positive, continuous, decreasing, everything's lovely, okay? So I'm going to jump right into the integral test. So to do the integral test, I'm going to, maybe I should write a little bit more detail here. So a sub k here is 1 over 1 plus k squared. And by the way, here, this problem, I'm doing it in terms of k, n or k. I don't care. You could even change it to n. I'm just going to write it this way. So that tells us that the f of x that we're going to use here is 1 over 1 plus x squared. So now if I'm going to do the integral test on this, I'm going to do the integral from 1 to infinity of 1 over 1 plus x squared dx. Again, that's an improper integral, so that's going to be, let's see here, the limit the limit as b goes to infinity of the integral of 1 to b of 1 over 1 plus x squared dx. So hopefully you guys are kind of with me here. Does that kind of make sense? So far, so good? Okay, great. Does anybody happen to recall what the antiderivative of 1 over 1 plus x squared is?
Arctan.
Boom! That is absolutely positively correct. So I'm going to make a little note here that if this is f, that right there, we'll call that f. If that is f, then, let's put it in blue, then capital F, which is the antiderivative, is equal to arctan of x. That is exactly right. So that's what we're going to play with here now. So we are basically going to do, let's go ahead and do it in red. So this is going to come to the arctan of, and I'm going to call it, let's do x still. And remember, we're doing the limit of this as b goes to infinity. And we're going to have to evaluate that from what we say 1 to b. So this is kind of interesting. This particular section is a nice little review, and you hopefully can appreciate why we had to deal with those improper integrals. All right. So that means that we need to do the limit. Oops. The limit as b goes to infinity of arctan of b, and then minus the arctan of 1. Now I'm going to do a little sidestepping here. What I'm going to try to do here is recall that the graph of arctan, this is the graph of arctan, looks something like this. Now what's important to know about this graph is that it has 2 horizontal asymptotes. Does anybody happen to know what the lower asymptote is?
Negative pi over 2.
Correct. And then therefore the upper asymptote is positive pi over 2. And we need that, right? We need to know that in order to deal with this first limit. Oh, by the way, when we say arctan of 1, we're basically saying the tangent of what is 1. And what tangent gives us 1?
Pi over 4.
You got it. So we are going to get minus pi over 4 here. Now, as our arctan function is getting closer and closer to infinity, what value does it approach? That pi over 2. So when we take pi over 2 minus pi over 4, we get pi over 4. Now, I kind of circled that. Maybe I shouldn't have done that. I'm going to clear up a little bit of space down here for myself. Let me get rid of this. And I'm going to answer the question. Let's do that in green. And I'm going to say that the series 1 over 1 plus k squared converges by the integral test. Now, you might be saying to yourself, Mr. Allen, why do you keep saying it converges by the integral test? Well, I have some bad news for you. Eventually, in fact, I'm just going to tell you in general, on the AP exam, they're not going to tell you which test. You'll have to tell them the test you used. So that's going to be the challenge. We're not there yet. You know, if you look at my last example here, you know, oops, let me go back here. I said using the integral test. We use the integral test because, I mean, that's what we're doing right now. And when we practice tomorrow, I'm going to basically say, hey, these you're going to use the integral test on. But eventually, I'm going to pull off the kid gloves, and I'm going to give you some series, and you're going to have to figure out which test you need to use. And there actually may be more than one way to do it. So that's where I have to be careful as a teacher. I need to make one comment. Actually, it's a very important comment. In fact, I think I made it in my notes. This right here is not that sum. Do you remember in the warm-up when we found the sums to be, I think the first one was 1/2 and the second one was like 3 3/4? Because we had a closed formula for the sum of a geometric series, right? This pi over 2 is only telling us that this integral is finite, i.e. not infinity. And since it's finite, that tells us that this series converges. This, by the way, pi over 4 is approximately 0.785. I'm telling you that this sum actually, and this is actually one of the most famous ones, I believe it's pi squared over 6. Let me double check that. Oops, did something wrong. Oh, I guess I need to put 6 in. Nope, I'm wrong. Disregard that. That's not correct. This one turns out to be, this sum turns out to be 1.07169. Sorry, that one's wrong. I'll come back to that one later because I want to make a point about it. But anyways, you know, the sum of this infinite series is this number, and I'm just letting you know it's an irrational number, which means I can't write it down. It's kind of like pi, but there's not a constant for this one, so it's just that, whatever that is, which is not equal to this, clearly, right? Now, you might be saying, Mr. M, why are you spending time on this? We just wanted to figure out if it converged. I know, but I just want to make sure that we don't get too far into this and realize most of the time I will not ask you what the infinite sum is. The only time I'm generally going to ask you what the infinite sum is when it's a
Geometric series.
There you go, geometric series. This is not the sum, is what I'm trying to emphasize. Most of the time, the question that they're going to ask you on the AP exam is, does it converge or not? In this case, it converges because the integral test produced a finite value, the integral did, therefore the series has to converge. This last example, what did this integral produce? Infinity. Therefore, it diverged. Okay, so I hope that makes sense. Actually, you know what? I think this is a good time for a poll question. Okay, I just hit a poll question here, and I'll give you a second to do that while I gather my thoughts for our next part of the presentation. All right, let's go ahead and continue on then. Hopefully you saw the poll question. Okay, looks like I have 18 people voted, and wow, amazing. You guys got that one right. So that's kind of a weak poll question. Sorry about that. All right, so we just got done with the integral test. Now we're going to start talking about P series. And this is the P series. So the P series is when you have a number. This number, n, is a real number. Actually, I should maybe write it this way. N is an element of the real numbers. So it can be any real number. And P is some, now notice that this is P, and this is P. And you know, I am actually saying this incorrectly. It's not a real number. What does it have to be? it actually has to be an integer, right? It has to be an integer. So that's technically this. Starting with 1, right? So we start with 1. So n is going to be 1, and then 2, and then 3. P is a real number. And that's what we're going to call a P series. So for example, if we look down here, this particular P series, we've got 1 over 1. Then we've got 2 over 1 to the first, if you will. And then we've got 1 over 3 to the first, if you will. So in this particular case, P is 1. By the way, we call this one the harmonic series. It's probably the most famous of the series. I find it very, very interesting. I think I've mentioned it before. Anyways, we'll talk more about it in a second. So let's look at another example of a P series. So yeah, actually, I'm going to come back to this. Let's go to this first one right here. So I've got 2 parts here. There's part A and there's part B. So let's look at part B here real quick, and I'll go back to the theorem, okay? It says P series with P equaling 2. So remember, so if P is equal to 2, we're talking about the sum from n equaling 1 to infinity of 1 over n to the P. In other words, well, n is 1, so that's going to be 1 over 1, but then P in this case is 2, right? So then this is going to be 2. P is 2. P is not changing. All right, so then the next term here, let's do purple, is going to be 1 over, and then n is going to be now, well, it's went up 1, so now it's 2. And our P value here is still 2. Then the next one's going to be when n is equal to 3. So that's going to be plus 1 over 3. Notice, though, that P is still 2. So we have that n is increasing. These are integers going up, in this case by 1, which is almost, it is what it's going to be for a P series. P, though, could be any real number. In this case, we just picked 2. Okay? So now I'm going to go back to the theorem, which is in this slide right here. And there's the generalized harmonic series, which is very similar. So it's similar. So we've got the summation. And instead of being 1 over n, okay, it's going to be some number like, I don't know, let's just pick a number. Let's say 3 plus, I don't know, 7. I don't know. And it doesn't actually even have to be whole numbers. These could be, 1, 5 or something like that. So anyways, they're the general harmonic series. I'm not going to worry about that one too much. It's called harmonic series because of its relationship to music. Anyways, so here's the theorem that you need to know. This is an important slide right here. This is an important slide. The convergence of the P series, and you guys will often see me abbreviate it like this, PST. Can you guess what that stands for? P series test. You'll often hear me refer to this as PST, P series test. And here's how it works. It's actually, I just went through an example of a P series. Here's what you need to know. It converges when P is greater than 1. Diverges in all other cases. Let me say that again. For a P series, if P is greater than 1, it converges. If it is less than or equal to 1, it diverges. By the way, does anybody know why it can't be negative? Why are we not talking about negative?
Because you can't have a negative on the bottom.
Yep. So once it's negative, it's going to move up to the top. This kind of gets into some interesting discussions when there's this thing called the Riemann zeta function, but that obviously is beyond the scope of this class, even though I think it's pretty interesting. Let's go back now and look at our examples here. In fact, let's just go ahead and do example B here first, since I started with that. So it's telling us that this is a P series with P equaling 2. So I've listed this out. In fact, I haven't done a very good job. I should probably do that, right, to make sure you realize that's infinitely many terms. And does it converge or diverge?
Converge.
It convert. Why?
Because it's greater than 1.
There you go. So you're done. And I'm going to show one more step here, even though I don't need to. This is 1 plus 1/4 plus 1/9 plus 1/16 plus ... This is going to converge. I'll put series converges since we have a P series. I'll call it P. Let me write this a little bit differently. I'm going to try to write this more compactly. Series converges by PST with P greater than 1. That should do it right there. So the beautiful thing is when you see a P series, you should be licking your chops because it's one of the easiest ones. I mean, the geometric series is right up there too. And actually, I should probably mention that right now. You want a little piece of advice from Mr. Allen? Here's the advice. Try not to confuse P series and geometric series. Do you guys see how that could be easily confused? Because remember, in the geometric series, if the R value is less than 1, it converges. Here, P greater than 1 converges. So it's easy to get. So that's a little tip from Mr. Allen, and you can take it or leave it, but it's good advice. Okay, so let's go back up here and deal with the harmonic series. By the way, what is P on the harmonic series? It's 1. So for the harmonic series, P is equal to 1, and that series would look something like this, n equaling 1 to infinity of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4 plus ... That's the harmonic series. Converge or diverge?
Diverges.
It diverges. Why does it diverge?
Because P is equal to 1.
Correct. I'll say diverges by PST, and P is less than or equal to 1. I am not going to go through a proof of why the harmonic series diverges. I will just tell you that I do not find it intuitive at all that it diverges. It seems like it should converge, doesn't it? In fact, let me make one more note on this before I move on to the next slide. What is the limit as n goes to infinity of a sub n?
It's 0.
It's 0. So do you remember when we talked about the divergence test? Here's an example of a series where the limit of a sub n goes to 0, but the series actually diverges. That's not very intuitive. Okay, so anyways, any comments or questions on these two examples? Okay, so we have one more idea here that we need to cover, and then I will give you the exit slip, and then you guys can either stick around and ask me questions, or we can move on, okay? Any questions? All right, last idea. And guys, I put a star on this one. Let me write it this way. This is, let's say, bonus. I'm not telling you that this is, the star doesn't mean that this is super important. It just, this is bonus. I probably should have put something besides a star. The big ideas today are the integral test and the P-series test. Those are the two big ideas. And honestly, I don't think they're super hard ideas, particularly P-series. P-series is a piece of cake. That's actually a good way to think about it. P-series, piece of cake. Anyways, so this actually goes back for a second. If you guys don't mind, I'm going to go back to something that we've talked about way back in chapter 4 So it's been a while. So let's just say, in fact, I wrote an example down here, and I'd like to maybe do that. So let's say that I have n equals 1 to infinity of 1 over n squared. Is this a P series? Sure, it is a P series, right? Here P is 2, right? So is it going to converge or diverge? Well, it's going to converge, agreed? So fair enough. Now what I'm going to do is I'm going to list out some of the terms here. So 1 plus, and then 1/4 plus 1/9 plus 1. In fact, this is the exact same series we just discussed. But now here's my question. What's S sub n? And in fact, let me do this. Let's change that. Let's not do S sub n. What's S sub 4? What does that mean, S sub 4? This is review.
What's the sum after 4?
That's right. It's we call it the partial sum. That's exactly right, Jack. This goes back to section 8.1. And I'm just going to tell you that this partial sum is 1 and 61 over 144, which is approximately 1.424. Okay, fair enough? Now, is that the entire sum? No. Okay. In fact, I told you that in general, we are adding infinitely number of fractions, right? So this number is probably irrational. We probably could never write out all the digits, right? So here's my question. How much error is this when we compare it with, remember, when I just write S, that means the infinite sum. My question is, how close is this to this? So if we went back to chapter 4, which I really don't want to, but just to remind you, we had this formula right here. R stands for remainder. So if I want the remainder of this sum after 4 terms, well, the remainder has something to do with the rest of those terms, right? And it turns out that the remainder of after the 4 terms is the sum minus what we started with. Does that kind of make sense? This number here, we don't know. This number we do know. And we know that what's left over has to do with all of this stuff over here. All of this stuff is like the remainder, if you will. Agreed? Which, by the way, we'll never be able to actually completely put our finger on in this case. So what this formula is telling us is as follows. It's telling us something about the remainder. And it gives us an upper and a lower bound. And that's what this is doing. This is about determining the accuracy of an estimate. So if I want to determine how accurate this guy is based on what we know in the first 4 terms. So in fact, here, let's just do this. So my question is where is the remainder at? I want to know between what values, what do we got here? How accurate are we? Well, we'll just use this formula here. By the way, in here was 4, correct? So what would be 4 plus 1? Well, that'd be 5, right? So I would need to integrate from 5 to infinity of f of x. And what was f of x here? Well, that'd be 1 over x squared dx. And similarly, on the other side, what's in here? Well, it's still 4. So this is going to be the integral from 4 to infinity of 1 over x squared dx. And I claim that the remainder has to be between those 2 values. Now, guys, I don't want to spend a bunch of time integrating this, but you guys would realize that those aren't really hard to determine, right? It's actually pretty easy. This one turns out to be 0.2, and this one turns out to be 0.25. So I've actually done an example of using the theorem right now. In other words, this value right here is no more off than these 2 numbers here. So the worst it could be on the upper end, off in terms of the upper end, is it could be a quarter. It could be a quarter off, 0.25 off. It has to be at least a fifth off. Does that make sense? This is not the sum. These do not equal each other. This is an estimation. Is it a great estimation? Is this a great estimation if we know that this remainder is between those two values? It's not a great estimation. However, I could tell you that that sum, could this sum here, could S be equal to, let's just say 2.1. Could S be 2.1? No. Why not? Well, because we know the remainder has to be between 0.2 and 0.25, which means the worst it can be off is add 0.25 to this. Does that make sense? So this, not even possible. All right, so I'm kind of good. I got 5 minutes. So here we go. I'm going to finish up, do this last example here, and then I will give you the exit slip. I'm really glad I did not show you the video because we would have ran out of time. So this is a question that you might see on the AP exam as a free response. How many terms are required to ensure that the partial sum for this series is accurate to within, remember this is 10, hundredths, thousands, 10 thousandths. So we want this to be within 5, 10 thousandths. 5 10 thousandths accurate. So how many terms do we have to go? In other words, we want the remainder, let's call it n. We don't know what n is, right? We want the remainder to be less than or equal to 0.123 and then a 5. That's what we want. But what does our remainder have to be less than? Well, our remainder has to be less than this. In other words, the integral from n to infinity of 1 over x squared, x cubed, that was the last example, was x squared dx. Now, this is an improper integral, right? So this is going to be the limit as b goes to infinity of the integral of n to b of x to the negative 3 dx. So moving on from here, I'm just going to put less than equal sign there. We are going to have 0 is less than 1 over negative 2 to the n squared. And this should be a minus as well. Now I'm going to pause here for a second. Do you guys understand why that's a 0? So you've got essentially 1 over x to the third, right? That's going to become a fraction of negative 1 over 2x to the second, right? What's going to happen to that 1 over negative 2x to the second when n goes to infinity, or when b goes to infinity? Right? Because the top's 1, the bottom's going to infinity. So does that make sense why that's 0? So this is equal to 1 over 2n squared. That's going to be positive now. In other words, I'm not sure where that came from. Here's that. In fact, let's do this in green. In other words, we need 1 over 2n squared to be less than 0.0005. We'll just put less than or equal to. And then you could, cross multiply, work all this stuff out. It turns out that n has to be less than or equal to 31.62 to 7, if I'm not mistaken. So basically, you're going to multiply both sides by 2, Then you have to cross multiply. Then you have to do the square root. Anyways, you'll get this value here. Oops, I forgot to flip my sign here. This should be flipped. So what's the answer? Will 31 terms do it?
32.
You need to do 32. So the magic number here is 32. Now, guys, they're going to ask for the minimum number to get the accuracy that you want. And I don't know if, I'm sure someone out there is a robotics. Is there any robotics people in here? Yeah, I know Sam is. Okay, anyways. How accurate do you guys need stuff to be when you're doing your robotics stuff? Like when you're cutting things, like what's the accuracy you guys shoot for? Do you guys know? You may not, maybe you don't know.
Usually it's like 1,000 at most.
1,000th. Okay, good. So usually for what you guys are doing, you just need 1,000. So that's 10th, 100, 1,000. So this is the accuracy that they might need when they're cutting. And by the way, guys, you realize you can never truly cut anything precisely, right? There's always an error. That's kind of what we're talking about here. So in my example, let's say, and again, I'm pretending, let's pretend I'm NASA, which I'm not, but let's say I needed it to be within this accuracy. So this is way more accurate than this one, okay? Considerably more accurate. So I would need this to go out to 32 decimal places. Guys, another way to think about this is, you know, there's actually an infinite series that represents the number pi. You guys know that pi is an irrational number. It doesn't terminate. It has no pattern to it. It's infinitely long. They know, I think, the first few trillion digits of it. But if you need to know pi to a certain amount of accuracy, this is the technique that you could use to figure that out. And by the way, you probably don't need 32 digits of pi in most applications. You probably need far fewer than that. But if you did, this is what you would need to do. So guys, that's going to wrap up the lesson for today. I'm going to turn off the recording now, and I am also going to send you guys the exit slip. So we are now done.